Hello, and thank you for the opportunity to speak here today. I'm going to tell you about the joint work with Professor Fedotov. Our work is devoted to one-dimensional Schrodinger operator with small analytic, almost periodic potential. Here you can see this equation on the screen. Here V is the potential, H is frequency, theta is an ergodic parameter, and lambda is a coupling constant. If H is rational, the corresponding Schrodinger equation is periodic, and in the case of the irrational H, the corresponding Schrodinger equation turns out to be almost periodic. Such equations arise in modern quantum mechanics, in particular in solid-state physics. When studying an electron in a magnetic field in various semi-classical regimes. The case of a small lambda is a well-known classical problem. We are going to study this equation and this operator with the help of a renormalization procedure called the monodromization method that was suggested by Buslaev and Fedotov. The monodromization method arose in an attempt to apply Bloch-Floquet theory ideas to one-dimensional difference equation with periodic coefficients. Originally, it was applied to the studying of the spectrum, to the geometry of the spectrum of the Harper equation. In the monodromization method, along with the equation, with this equation, one has to deal with a difference Schrodinger equation that you can see below. Note that the solutions of the second equation are the solutions of the first equation if we restrict them on the set of the points h times k plus theta. When h is irrational, the spectra of the operators that correspond to the left-hand side of the equations coincide. On the other hand, the second equation, the difference Schrodinger equation, is periodic. And as in the theory of differential equation, one can try to construct its Bloch solutions. Bloch solutions are the solutions that are multiplied by a constant when you shift an argument on the period. It is convenient to rewrite the second equation in the following form. That is the matrix form. When studying differential equation, in order to construct Bloch solutions, one has to firstly construct its fundamental matrix solution, and then find for this solution a monodromy matrix. The monodromy matrix is the matrix of the operator of translation by one that is restricted on the solution space of the equation. It is defined by the following formula. Knowing the after the construction of Bloch solution, I'm sorry. Yes, of course. You have to solve this. Just a second. No, it's okay. I'm going to continue.
But I think Как говорите по-русски? Объясните, как строится матрица монодроми.
Просто, как сказать, мне было бы удобнее на английском продолжить, на самом деле.
Что?
Мне было бы удобнее на английском. So, we, just a moment. Firstly, one has to, in order to construct block solutions, one has to firstly find a fundamental matrix solution of the equation, and then one has to diagonalize the matrix, and if it is possible, then one gets a basis of block solutions, and the behavior of the block solutions at infinity is defined by the trace of the monodromy matrix. Now, having the basis from the block solutions, one is possible to understand the behavior of the general solution of the equation and define whether E is in the spectrum or not. In the case of difference Schrodinger equations, the monodromy matrix is still defined by this equation, but the solution space in the case of difference equations of such form, of that form, is a two-dimensional module of the ring of H-periodic functions. And so the monodromy matrix turns out to be H-periodic. So when one tries to diagonalize the matrix, he encounters the difference equation of the following form. That is another monodromy equation with new parameters. So we've reduced the problem to the problem of the previous form. And one can apply the discrete transformation to this new equation. And then another monodromy equation will arise. And so we have a chain of equations. And the properties of the resultant chain of equations are closely related to the spectral properties of the initial operator. Earlier, with the help of the monodromization method, mostly the equations were studied which potential is a trigonometric polynomial. Here we want to concentrate on the case that when the potential is analytic is in some neighborhood of the real axis. And we want to find out how the singularities that are located on a finite distance from the real axis affect the spectrum. And in our work, we've obtained the first results in this direction. We have proved two asymptotic formulas in two situations. And the first situation is the assumption for the first situation you can see here. Firstly, we assume that the potential is analytic in some neighborhood of the real axis, and we make no assumptions on the type of singularities that the potential has on the borders of the analyticity domain. And here, for the difference Schrodinger equation of this form, we get the following theorem. We prove the following asymptotic formula. So here, Z0 is a point in the upper half plane. Gamma 1 and gamma 2 are the contours that are located on the borders on the border of the analyticity domain. One can also see that the leading term of the asymptotics is independent of Z. and the error term is one periodic, and that is consistent with the fact that the monodromy matrix is one periodic. Also, we can see that the asymptotic formula implies that the determinant of the monodromy matrix is equal to 1. Having dealt with this situation, we consider the simplest case of the analyticity violation. That is, we assume that the potential is meromorphic in some strip, and it has a finite number of simple poles per its period. Also, here we have a notation that P is a period of the pole set. And under these assumptions, we prove the following theorem. Here we can see that the distribution to the monodromy matrix from the pole set are clearly distinguished. Also, we can see that the error term of the monodromy matrix now consists of two terms, and the first term is of the same form as in the first theorem. This is an integral term, and we also have another term that has the form of cotangent multiplied by residue of the potential.
То, что полюса добавляют.
Да-да. Also, we can see that the monodromy matrix turns out to be meromorphic in some strip, and it has poles in the set of the points that can be described as pi by h plus an integer, where pi is the period of the pole set. Also, I want to mention that Professor Fedotov has made a separate work where he studied general, that means non-asymptotic properties of monodromy matrix in the case of the potential that is meromorphic and has two simple poles per period. And the results that we obtain here, I agree that the results that we obtain here agree with his observation from this work. Also, I wanted to mention the case of a potential of a special form. This model, as you can see here, it was considered by some physicists, and also it was considered by mathematician Zhytomyrskaya. And the interesting fact about this model is that one can choose a basis in the solution space of the equation such that the integral term in the asymptotic representation vanishes. So this is an interesting model for us, and we're going to make a separate work on this model. So let me now discuss the way of the construction of the asymptotics. In order to understand asymptotics, one has to firstly construct two linearly dependent solutions of the equation. And because this is since the solutions, since the coefficients of the monodromy matrix are expressed in their terms. So let psi1 and psi2 be two linearly independent solutions of the equation. So the coefficients m11 and m12 are expressed with the following formula. Here W is somewhat analogous to Vronsky in the theory of differential equations. You can see the definition here. So how we construct the solutions? Firstly, we rewrite the equation in the following form. And since the lambda is small, it is natural to try to construct the solutions of this equation in terms of the homogeneous equation. So to construct the solutions, we somehow inverse the operator that corresponds to the left-hand side of this equation. And we consider an integral equation on the contour that is depicted here. And the integral equation that you can see below. So the integral operator here has the following kernel. One can see that the kernel has singularities away from the contour, but on the contour itself it is continuous. So the operator is well defined, and so firstly we construct the solutions of the equation on the contour itself, and then using the analyticity of the kernel, we can firstly analytically continue the solution to some neighborhood of the first contour where the solution was constructed. And then we can define the contour and analytically continue the solutions to the whole neighborhood of the real axis. After constructing the solutions, we find the asymptotics, and then using the formula, using these formulas, we understand the asymptotics of the coefficients of the monodromy matrix. So that was in brief the procedure for the case of analytic potential, but in the case of meromorphic potential, it gets a little bit more complicated, but we won't dwell on it here. So that's all. Thank you for the attention.
Questions, please. Что про спектр известно в ситуации?
Про спектр, как сказать, мы пока еще до этого не добрались, вот, но предположение, что сингулярный.
Сингулярный?
Да. Вот.
То есть полюса как на спектр влияют гипотетически?
Вот пока сложно что-то, ну, то есть я пока не обладаю информацией, чтобы сказать что-то по этому поводу, потому что мы только, так сказать, вот сделали подготовительный этап, и вот сейчас должны начать уже, так сказать, с этим разбираться. Вот.
А что, если лямбда не маленькая?
Если лямбда не маленькая, тоже пока ничего не смотрели, но вроде как это можно...
Но вам это интересно, это никакой тут неинтересный случай.
Да. То есть мы думаем, что это тоже можно рассмотреть, эту ситуацию.
Okay. If there is no questions, let us thank the speaker again.